Anna Förster from Universitet Bremen. Very much welcome, Anna.
Thank you, Frederick.
Yeah.
So, yes, just maybe a little bit about myself. Some of you have been presenting themselves very personally, very nicely. It's always very interesting to see what kind of people are sitting around and watching here our streamings and videos and everything. So my name is Anna Förster. I'm, however, native Bulgarian, grown and in Bulgaria, in Sofia. Then I moved to Germany to study computer science and aerospace engineering. Later on, I moved to Switzerland to make my PhD and to do also some postdoctoral years. And since now 2015, these are now already 6 years, more than 6 years, I'm at the University of Bremen in the very north of Germany, but still more south than Sweden, which is amazing. Typically, I'm the most north participant of something. I'm a professor of computer science and electrical engineering, and I'm doing a lot of work, especially in wireless communications, and part of that research is also in wireless sensor networks and Internet of Things. And today I would like to give you a small overview about what is that, what are the biggest problems, let's say, when we are practically doing those areas. Not only in theory, but we actually decide to do some applications, some implementation, some deployment. This overview is much more high level than the videos which you have on YouTube online. And the quizzes are not due immediately now, so you can watch this stream first and the videos and ask questions, and only then you can do the quizzes a little bit later. That shouldn't be a problem at all. Feel free really to ask questions. It will be easier for me if you tag me in your questions so that I know that somebody needs really my help. Otherwise, it's a little bit like I'm not very good at Discord. I'm the first time it's using it. So it will be good if you tag me so I know that it's my turn. Okay, so let's see what we have here. First of all, just a small overview of what we'll be talking today. Like, first of all, I would like to introduce to you what are wireless sensor networks and why are we talking about them in an Internet of Things course. Then we will be talking a little bit about possible applications all around the world. I have a very nice potpourri of everything which is possible to do with Internet of Things and sensor networks. We will be talking also about types of sensor networks, how they're related to different other areas or different other buzzwords, because there are a lot of them. And then we will go into two very important topics, which will not cover really deeply, but it's important that you're warned about them. The problem in general with wireless communications and what you can expect as problems there. And on the other side, about power management, batteries, and so on. As I said, it will be a very high-level talk, but you're welcome to ask also deeper questions in Discord later on. So, what is a typical sensor network? A typical sensor network consists of some sort of a couple from several actually, until tens of thousands of different nodes. We are talking usually about sensor nodes, but we interchangeably use the word sensors or just nodes for them. Typically, those are embedded devices which have everything on board which you need. They have some wireless communication. They have a microcontroller to do some processing and to coordinate the components. You have some sort of a battery, of course. You have some sort of an interface in order to be able to talk to these devices. You have maybe not some battery management, so power control, really. This is not necessarily, you might or might not have a real-time clock, so this is also some kind of a luxury. What is really important is that they're connected wirelessly to each other, so you throw them pretty much into the environment in a planned or unplanned way.
Maybe we could spend like the real-time clock. You mentioned that one. Why did you mention real-time clock
Because this is a big trouble, and it's something which students or beginners are very frustrated about. In a normal computer, you always know what's the real time, so I can watch it here on my computer and can tell you it's the 16th of June, 1806.
Yeah.
And on such a device, if you don't have a real-time clock, which is a special component with its own battery, and you have to connect it, you actually don't know what time it is. You only have the so-called local time. Local time means the number of seconds or milliseconds, depends a little bit on the device, on the microcontroller, and on the precision, from the last restart of the device. So if I ask that timer, let's say, it will simply tell me 4,000 after last restart. And it's very often that I cannot make any use of that.
Yeah.
So that's why I mentioned real-time clocks. This is one of the pains in embedded computers.
Yeah, and we can mention, I mean, an Arduino device doesn't have a real-time clock, and actually not the PyCom device either. So you can buy an additional one from, that's totally possible.
Yeah.
But I guess most of our students now really don't have to care about that. It's really, but it's very good that you mentioned it, because there might be good to know the constraint already in the beginning.
Exactly. So such constraints are actually very, very popular here. Like everything which can be get rid of, we got rid of it. That's why you don't have typical real-time clocks. You have only a very rudimentary power control, which means that even your power is not regulated and you can get some overpower or underpower. All of these things are considered luxury. And the reason is really price, because especially in the first vision of wireless sensor networks, as it came up like 22 years ago, it was that it's as cheap as possible and that you can afford really to throw it out in the environment and just forget about it. Of course, this is not practical. And this is absolutely not sustainable solution, but that was at least part of this vision of also the so-called smart dust. You might have heard already about that. So this is all part of this concept at the end. So just to continue here, the nodes are wirelessly connected to each other, and we'll be discussing all these problems a little bit later. And typically you have also some sort of a dedicated node, which can have the same hardware or a different one, that doesn't really matter, which is serving as a kind of an entry point to the outside world. And this is probably also the biggest difference between a wireless sensor network and the Internet of Things. In a wireless sensor networks, you have a whole network where only one entry point to the internet, or several, but they're dedicated and they're few. And in the Internet of Things, you kind of assume that all of the nodes are directly connected to the internet, even if that rule is also getting more and more approximate over the years.
Yeah, I would say that. I mean, that must be a very large gray area, because when you talk about like Zigbee, Z-Wave, you could almost say that they fall into the category of Internet of Things. Right. I guess that's a very broad category. So, and LoRaWAN networks for sure. That's Internet of Things. So
exactly. So there is a huge overlap here, and that's why I'm still talking also very gladly about wireless sensor networks, because this is sometimes covers it or describes the application a little bit better. Sometimes it's really the Internet of Things clearly, and in most of the cases you cannot tell them apart. Exactly. So what is really important about sensor networks or about Internet of Things is that the resources, exactly as we were discussing, like all possible resources, also in terms of power, in terms of processing, in terms of in terms of memory available, and so on and so forth, they're very, very limited. So you would like to have these devices cheap, you would like to have them simple, and that brings all of these resource limitations with it at the end. Oops, sorry. One big problem is that the wireless links are actually spontaneous and they're not really planned. So if you put the nodes in some way into your environment in a way that, for example, it covers a particular area or particular interesting spots, which you would like, for example, to monitor or to cover for some other reason, you actually do not plan your wireless connections. So some of those nodes will be connected to each other very nicely, and at very large distances, and some will not connect to anything at all, whatever you do. Typically what a sensor network does, and this is also exactly the same also for the Internet of Things, is that the network senses some sort of phenomenon. So for example, either it interacts with the user and senses some input from the user, or it senses temperature or humidity in agricultural scenario. So something is sensing. This is very important. And then you transfer the data to some sort of another user. That user can be another machine. It can be a real user to visualize the data and things like that. And really the biggest part is always sensing and sending. Sometimes there is also some sort of an actuator, for example, open up the heating valve or something like that. But this is sometimes there, and very often it's actually limited to this sensing and reporting or sending. Some applications which are well known and very popular nowadays already, probably one of the first ones was the Vineyard Monitoring. Here a picture from Hungary. It was one of the first applications because Vineyard are very, how to say, like they have two big troubles. First of all is the irrigation of the fields. Like you would like to irrigate them as little as possible, but you need to understand the stress level actually of the plants. And on the other side, exactly that same stress level controls also the usage of pesticides and herbicides, because only with this data you know how little pesticides you can actually use in order to keep your plants healthy. So here typically we very often have an external power source, like here a solar panel. This is typical because vineyards are in the sun. And you have some temperature sensing, you have some humidity sensing, you have also some very specialized sensors sometimes here, like a leaf wetness sensor, which really looks like a leaf and it has similar properties so that you know how much humidity is standing on the leaf. This is very important for sickness recognition. So a very typical one where you have many of those sensors. They're not connected directly to the internet because there is no need for that. They're connected to each other and to some sort of a sink or central station, which then gives you all of the information further.
This is also, I mean, also that when they are not connected to the internet, that is one advantage of that, or, I mean, it could be a security advantage as well.
It's a security advantage, it's a price advantage, surely, because here you can use also wireless technologies, which are much cheaper, and they are much more power efficient than, for example, connecting directly to Wi-Fi or to 4G or something like that. So it makes it simpler.
Yeah, and yes, I mean, we are going to talk more about wireless networks. So we have like sections on that later on. But in this example, the vineyard monitoring you have here is what kind of wireless technology are you showing here?
Well, when these pictures were there, and I think in this particular application, they were using Zigbee-like technologies, like either Zigbee directly or Zigbee is based on another MAC standard, which is called IEEE 802.15.4. And this is an extremely popular, simple MAC protocol where you can build on top of it whatever networking layers you would like. And this was a very popular solution in those times, that you just take the 15.4, as we call it, and you put some sort of your own hand-tailored routing networking solution on top of it. But at the end, people also used a lot of Zigbee. Nowadays, probably people will turn to LoRa or to Sigfox, which we will see many times in this course.
I got a question here about the data limits on different categories of LoRa Wi-Fi. Maybe we don't have to spend so much time to elaborate on this, but maybe we could just mention something about it.
Okay, in general, what we say is that the Shannon capacity, the capacity model, which tells us pretty much in very simple words that the higher the frequency, the more your data throughput, but also the less your transmission radius. So if you put something like Wi-Fi, you get normal data rates as you're used from home, so megabits. And however, the transmission radius is very small and you need a lot of power. Zigbee is a kind of an intermediate solution, which is lower data rate. It's still at 2.4 gigahertz, but the lower data rate makes it a little bit more power efficient. The transmission radius is bad, like several tens of meters is all you can achieve outside. And then LoRa, for example, that supports in Europe the 868 megahertz or the 433 megahertz. And depending on those, you can go really hundreds of meters apart or even kilometers, like for the 400 channel. And there the data rate is, however, extremely low. And now the question is what you want. If you have something like this, where you submit some sensory data, which are a couple of bytes every 15 to 20 minutes, then you can go definitely for something like LoRa, and then you save a lot of energy and you have a huge transmission radius.
Yeah.
If we have something like accelerometer, we'll see that in the next application, then you're probably bound to something which has a proper data rate.
Yeah, so it all depends on your application. So yeah,
all
we are going to. I mean, this is like a broad lecture. We could probably spend an hour on just this topic. So I'll let you continue from that question.
There is one very interesting question which just popped up here in Discord, whether this can work out of the box or it has to be customized for each installation. It's somewhere in between, I guess. Like there are many solutions nowadays from various companies which are really working out of the box, but the installation is not really simple. So a vineyard person who is more, like a farmer, they might have some troubles installing and setting it up. But yes, it actually works out of the box if you know how to follow that relatively complex installation manual.
Yeah.
It's a very good question, actually. Okay,
Yeah.
Let's continue here because I have also other very interesting application. For example, this one. This is very typical one again, where you would like to do some construction monitoring or structural monitoring. Here in this case, it's a bridge, which is a very popular one in Greece, and it's some kind of special because it's hanging. Most of the parts are actually completely hanging. And they actually had some problems in the beginning and they had to close it down because it started vibrating and really shaking up and down by several meters. They closed it immediately and they installed actually a sensor network on that. And that's a very interesting application just to talk about exactly data rates, because the only sensor here they have is acceleration. So you would like to give accelerometer data, which are very data intensive, and you cannot do any processing on the edge, as we're saying, like you cannot do processing on the nodes because these are very heavy processing algorithms. So you have to transmit everything first to some kind of a server and then process the data in order to see whether everything is normal or not. And here also delay starts playing a role. In the Vineyard monitoring, nobody really cares whether I get data immediately or an hour later. It's never about such immediate delays. Here, it is extremely important that you get, of course, the information about some anormal vibration as soon as possible, like seconds or at most minutes after it has occurred, so that you can do something against it. So let's see what else we have here. This is also something very interesting and again completely different. Like the devices are extremely similar, but at the end you have completely different properties. These are cows in Australia. And the idea is that you actually can build virtual fences with those. So you can program a system which controls the areas where the cows are grazing. And once they're trying to get also by the normal fences, and they know that they have to turn back and go into their area again, which is very cost-efficient solution, especially for big farms, because they don't have to use any kind of fences and they can always see also online where the animals are. And you can even do some really nice and sophisticated algorithms on top of that. For example, if a cow is not moving for some time, probably it's sick and you should go and check on it. So it can do all possible things. And at the end, what they have are these collars where you have a GPS on board, you have some battery on board, and you have also some health data like temperature and I think only temperature actually. And then you have, of course, also acceleration, so that you understand also how it moves. Like GPS is not precise enough to give the movements actually the cow itself. And you have an actuator. This is the first time we actually have here an actuator. Everything else was just monitoring and signaling a problem, and then people had to do something about it.
The actuator in this case, that's like an electric shock or something like that. Okay, yeah.
That's how you do. I also don't want to wear one of these colors.
Yeah.
So this is an example from my own research. We're specializing some kind in underground soil monitoring, which is also I'm very enthusiastic about this project actually. It's very nice. We have been developing it since I came here, since 2015, so now for 6 years. And we developed even our own hardware platform, which is called MoleNet. And the idea is to monitor different properties underground. The problem with underground, what happened? Sorry. The problem with underground is that you would like to actually bury the node. That's done for security reasons. You would like to hide the node. You would like also to have the properties really underground and not on the so-called topsoil, but you would like really to go downstairs. And here is some information, like some data which we got from Cameroon. There we have been pretty active in developing such sensing monitoring applications. And you can see here the usage of this data. So this is soil moisture, which is completely different behaving as normal air humidity. You can see here actually very nicely. Can you see my pointer?
Yes.
Okay, very nice. So you can see here that it was pretty constant over 2 days. So nothing really is changing over the period of the day, for example. Then there was a very nice rain, which increased the soil moisture to some other value. And this is what agricultural people or farmers are looking for, a rain which stays afterwards in the soil. And here is the opposite example where you see that there was some rain, but it was drained almost immediately to some lower value again. So this is a bad rain. This is one of these floodings which takes everything with them, including nutrients from the soil. So this is also a very interesting way of looking into that. And
but let me say, that is the measuring conductivity in the soil, or
correct.
Yeah.
Yes, there are special soil moisture sensors which are at the end all not all, but most of them are conductivity based.
Yeah, and I guess that many actually, I think, are inspired by just this example. I see comments about the vineyard and such, that and also speaking from experience since last year, that a lot of projects were actually agriculture projects, that were greenhouse projects. They were monitoring the tomato plants and a lot about water. And I think there were farmers in the last year that measured how much water the horses had and such. So yeah, so a lot of like these interesting use cases. And as I must say that the more of these cases, the happier I am, because then you can actually show the sustainability part of the IoT, that you all are making the world a little bit better and not worse.
Exactly. You have lots of possibilities which otherwise take a lot of money, a lot of effort. Here you have always a very cheap, a very self-made solution which can be done by local students from a computer science department. Like in this case, we had the help of the computer science department in Gaoundéré in Cameroon, with a little bit of knowledge and a little bit of supervision and a little bit of a budget, similar to the PyComs which we have here. Like the price is really not higher than that. You can actually make a difference. And this is really cool. Like I have here also another very nice application of the same. Now, for some reason, I cannot go further. Okay, doesn't let me go anymore.
I can show a picture while you try to see if you can change that. We are two on this presentation. So, and you showed a bridge just earlier on. So I was just like trying to link that to the different cases of IoT. So this is just a classification from Ericsson, and you can find a lot of these colorful pictures online when you Google for IoT. So but when we're talking about cheap sensor networks, I guess that we are also talking about the area of massive IoT. So it might be too many things to consider now, I'm sure about that, but we are talking about definitions and we're talking about a broad area. And if we're talking about 5G, for example, that could absolutely be IoT, and it is IoT. But then that's not the technology that is best suited for sensing the soil level in a farm, because that needs to be cheap and run on power, like on battery for a long time. So the area we are in is like in the massive IoT area, I would say. So if we're going to look at this picture and point on where are we in this course, I would say that you are in the left end of this picture, the massive IoT. So low data and battery. So you all get some kind of feeling on okay, what are we doing? What kind of IoT are we going to do? So let's skip back to you again, Anna.
Thank you. There was one of the slides just didn't want to come with me. So this is a very also exciting application here, and again, a very interesting example of what kind of weird applications you can have. This is the Maricultural Institute in the University of Namibia, and they had a very special problem. They are trying to raise sweetwater fish in salty water. They do that in big aquarium. And they have, of course, to monitor very exactly the saltiness of water. They have to monitor the pH value, the temperature, and the dissolved oxygen. And this is all you can see here on this site. This is, again, our MoleNet hardware working at a lower frequency, like we have a normal RF transceiver, but at 433 megahertz. And we used it in this example because in this room of the aquariums, it's very wet. It is not really underwater everything, but it's very splashy, springy, extremely moist air. And so we decided to use again this very low frequency so that we have a better penetration through the air. And that was very successful, actually. This is an example of what we were able to detect. There was a small leak in one of the aquariums, and our system immediately signaled an alarm that the temperature is rising extremely high. And this was because actually there was almost no water, and the fish, of course, were left only in this small pond here. But they didn't die. We managed actually to save them. So this is yet another interesting example. And again, something which we have tried with our hardware is to find trapped miners. This was an application in South Africa, where the question is, if part of the mine collapses, how to find the miners again. And typically the collapse is relatively small, but you have no idea where the miners actually are after that block. And we tried it out with, again, our hardware to see how good that can work. So here you can see a small mock-up mine, which is just below the university, and it's mimicking pretty well the conditions in a real mine. And here we put lots of stones. These sacks are put lots of rocks at the end inside, and we have buried our sensor nodes below. And we were able pretty well with the lowest frequency actually to understand where the miners are. And it was pretty clear, for example, from this graph, you can see here two experiments, one at 800 megahertz and one at 400 megahertz. And you see that with the 800 megahertz, 10 meters was the most which we could transfer the data, and later it just doesn't penetrate the rocks anymore. And on the other side, with the 400 megahertz radio, we were able to penetrate up to 60 meters, which is already quite good and almost there where we would like to go. Okay, that was a small app which was connected to that so that we can actually see where the miners are. And you can see here the small miner and where it is approximately, like you can do only with RSSI measurements. RSSI stays for Received Signal Strength Indicator. That tells you how strong the signal is. You can actually localize the miners. You can compute where he or she is, mostly he. So this is a very recent application, and it is a pure Internet of Things application. We have one single sensor here. So people have typically even asking me, why is that an IoT application if it has only one single node? But I still believe it is a very nice application. It's a tea factory in Kenya. You see that I'm a lot in Africa. And here we have a camera above the tea fermentation bed. We're taking pictures. And in these pictures, we use a deep learner, a deep neural network, in order to decide whether the tea is still under fermented, it's just perfectly fermented, or it's already over fermented. And we're signaling that to the workers so that in case they make, for example, a break or just not pay enough attention, they know that the tea is ready and they don't have to sit the whole time there. So it's an optimization of the process itself.
What kind of hardware do you use in that case?
This is a Raspberry Pi with a small camera, like a normal webcam. And everything is done on the edge. So it's directly here in the factory. It's not on a server outside. But the edge is actually, well, it's the Raspberry Pi.
Yeah, but that's powerful enough, because we have played a little bit with the Coral boards, and those are like, you get, I think, even more than a tenfold, or maybe even more than that when you're running the TensorFlow Lite models. So.
Well, what we did, of course, is that we also use TensorFlow, but what we did is that, of course, you train your network offline, and then you only reuse the network here. So otherwise, the Raspberry Pi will, of course, not be able to make the training, but the classification only, it works actually very nicely. And you see also that the pictures are quite nasty, like even for a normal person to recognize what is what and to say, well, this is clearly over fermented and this is clearly perfect. It's a matter of expertise, really, to recognize that. Like, to me, it's all kind of similar. And here you can see also our very simple architecture at the end. So here you have the Raspberry Pi, you have the Pi camera, and we have still Wi-Fi here on board, actually. We have the edge server, and there is, of course, a connection later on to the internet, so that for pretty much statistical reasons and for monitoring reasons.
But it's super interesting that you took that you planned to have just this example, because there are questions about, oh well, I think I need like a high rate of data, and as I see it, there is actually parts in this course now which, like, I've put in just because of the interesting new applications you can do when you put a lot of computing power on the edge out there. And also there are some consumer hardware which are really cheap. I'm just going to mention there is an OpenMV. I can drop a link in the chat. I think it's about $50-$60. You can run TensorFlow models and program them with MicroPython. And it's a little camera. Well, it gives you some possibilities.
Yeah.
So.
What is important is that, like, first of all, this is a typical hardware for any IoT device, sensor node, whatever you call it. What is really important is actually how much power you need for each of the components, because you can always measure one device, what the power has in general, what kind of power it needs, what kind of current, for example, it consumes. But it's more important to look into the individual components in order to know which one should you use only sparingly and which one you can just say, whatever, I can leave it on. So let's look here into this example. We have the microcontroller in the different modes, active and sleep, and you see that it's already quite of a big difference between 1.8 milliampere compared to 5.1 microamperes. But what really strikes us immediately is, first of all, the external flash, which is very expensive, 15 milliamps, compared also to the receiver, to the radio receiver, which doesn't matter actually receive or transmit, it needs almost 20 milliamps. This is also something to very interesting discussion. People usually react like, just a second, transmitting is actually kind of should need more power than receiving. The answer is no. Maybe you should think about another analogy for that. When I'm talking, yes, it is quite difficult actually to talk. Of course, I need a lot of energy. But if I have to listen to somebody in a very noisy environment, that actually feels even more power hungry. So this is the right analogy here, because the transceiver needs a lot of power to filter out all noises, to compare different signals which are coming in, to make them one signal, and so on and so forth. So this is very, very energy hungry. And just to discuss also what does it mean. Here we did a small experiment with some normal AA batteries, as everybody knows them. We connected a normal sensor node. It was also the Z1, I believe. And we waited with different duty cycles. We waited for the node just to die. First of all, we like this green dashed line here represents what we expected from the data sheet. Like, you simply take your table about power consumption, you take the capacity of the battery, you do some little math, and you say, okay, I expect my node, for example, if it's sleeping, if it's working only 25% of the time, then I expect it to last more than 500 hours. In reality, it was not even 200. And the same we did for 75 duty cycles. So this means that 75% of the time I'm on and working, all components are on. And then for 100%, this is the most you can go. You don't sleep at all. And you simply see how big this difference is. So this is just to say, be careful about such calculations, such dry calculations, because they will typically not provide you with the right information. There are, of course, lots of good explanations why that happens, but for somebody who is not an electrical engineer and doesn't want really to know why that happens, just remember that it happens. And what is important is always to have such a table in mind, and to simply know that these are really the two power-hungry components. It's the transceiver, and it's interestingly the external flash. So also this one has to be used very sparingly, and not just every byte which you gather, you just write it to the external flash. You will go out of battery very, very soon without even knowing what's happening to you. So another big problem is connected actually to the power control on the sensor node. So a good computer or a good device in general has power control, which controls how much power is exactly available to the whole board and to individual sensors, to individual components. And it actually switches off the complete device if not enough energy is given. So that we already discussed it many times. We spare that out because it's an expensive piece of hardware. This is one of the reasons. The other reason is that actually the sensors or the components, they work quite a long time after their specified voltages. And we would like to get also out that piece of, let's say, efficiency. So here we have another experiment where we have regulated very exactly the voltage to the sensor node. And you see, like, actually it is supposed to be working only until 2.2. This is where we started the experiment. And below, it's supposed to not work at all, but this is not true. It continues working very nicely. This is actually the temperature sensor reading now. It continues to work very nicely for quite a long time. And suddenly it starts giving you wrong data. And this is something extremely nasty, because towards the end of the lifetime of a node, of a device, you start getting weird things which do not make any sense, but you cannot automatically detect them that easily.
But I mean, this obviously depends also on what kind of sensor you're talking about. So in this particular case, did you mention what kind of sensor?
This was just one of these DHT11 temperature sensor, just one of these which you find in almost every device, actually. Of course, it depends on the sensor, clearly. Like some of them will really stop working. Most of them continue sending you some sort of data, and that data just doesn't make any sense. And sometimes this is obvious, sometimes it's not. So for example, here, this small increase in the beginning can be very well due to starting fire, or this whole thing, this whole area here. It can signal you that you have fire in the kitchen, but you don't. You just have a device which is dying. So this is something which is very important just to keep in mind, that towards the end of the lifetime, weird things start to happen. And if you see them, it's probably better just to change your batteries and see whether it's still happening.
Yeah.
And this is what we call debugging. Okay, so this is actually for today. We also used a lot of our time. It was a very nice discussion. I would like you pretty much to remember 4 things. First of all, we're talking about small, inexpensive devices with all of their advantages and disadvantages. We have tons of possible applications, and there are no limits to your creativity and to where you would like to use them. We do have wireless communication problems, and we do have power problems. And those two just have to be kept somewhere on the back of your mind every time you're getting something which is kind of weird, kind of unexplainable.